Okay, guys, we're going to be going over Chapter 20, Section 1, which is 574 to 579 on waves. So have those notes out, do your usual highlighting and writing things down that you don't have, knowing that we'll probably have a test on all of this. So first thing we need to talk about, generally speaking, is what is a wave. So some characteristics are that they are a disturbance in a solid, liquid, or gas, and energy is transmitted through a medium usually when you have this going on. So what is a medium? We have to talk about that in just a minute. So as the wave travels, it does work on everything in its path. So a medium is the physical environment in which the phenomena occurs. So it might be through air or water, and a lot of waves need to have a medium to be able to travel. So that's a big deal. If you don't have a medium, some won't be able to travel. So again, it could be a gas, liquid, or solid. A good example of a wave that must have a medium is a sound wave, because there has to be vibrations off of the medium. So if it needs a medium, we call them mechanical waves. So a great example would be sound waves, right? Some don't need a medium. We'll be talking about the electromagnetic waves on the electromagnetic spectrum soon, but those are things like light, X-rays, radio waves, all sorts of ones that we'll talk about when we get to that. So you should know the two main types of waves. We have what are called transverse waves. And if you think about a wave moving on a rope, when you hit the rope up and down, that's a great example. I'd be showing you that if we were in class right now. Instead, I'll show you a picture. The particles of the medium move in a transverse wave, and they move perpendicularly to the direction the wave is traveling. So the high points are called crests. The low points are called troughs. I always think of animals drink from a trough. They put their head down and they drink in a trough. So that's the low point. So as you can see here, the crests are kind of the orange pieces here, and the troughs are the green, or excuse me, the orange pieces that are at the bottom. And the green is kind of letting you know other parts of the wave, so that if you were moving this, you would see that they would move with it. So the wave travels to the right, moves to the right, and the person is moving their hand up and down while it's connected to the doorknob there. So it says a wave on a rope is a transverse wave because the particles of the medium vibrate perpendicularly, right? So opposite, right? Up and down versus right and left. So the second type are called longitudinal. These are where the particles of the medium travel parallel, right? Not perpendicular, but right along with the direction of the wave. They have what are called compressions. So that's where the particles are really closely crowded together, and I'll show you a picture of that in a minute. And then we have rarefactions, where the particles are spread out. So think of a slinky right now, because that's the visual that we would be using in a classroom. So you can see here they're going to compare longitudinal and transverse. So the longitudinal is up here, and you can see the really close together parts are those compressions, and they show you a couple of them along the way, and they are labeled. And then the rarefactions are where, think about that slinky being farther apart, the coils being farther apart. So that's a great example of a longitudinal wave. And then the transverse, they're showing you the troughs and the crests are going to look a little bit obviously different in a transverse wave. So sound waves are longitudinal. They're going to travel by those compressions and rarefactions. Now it's too bad that we can't visually see a sound wave as it's moving across the room, but this is what you would see. I really like this picture to explain it. So they have a drum head, right? And they're showing you that as the sound comes from the drum head, you can see the compressions and the rarefactions. The compressions are these darker gray areas that you see, and as it moves, right, the compressions move out. They're over here, and you can see the rarefactions are kind of where it's not as gray in between, right? So sound energy is carried away from a drum, right, by the longitudinal wave through the air. So, of course, the medium is the air. We need to mention surface waves. So that is a wave that's going to form on or near a boundary between two different media. So think about, for example, the air and the water. Ocean waves are great examples of sound waves, or excuse me, surface waves. Ocean waves are a great example of surface waves. So a floating bottle shows the circular motion of the particles in a surface wave. So they move in circles, surface waves do, rather than up and down like what we've been talking about. So the particles move forward at the crest of each wave and then backward at the trough. So that's kind of a cool visual there. You can see the movement, how it goes as it moves across. So that's what I have for you on the first section. And now we'll go over the second section. So turn to the properties of waves. So a couple terms that you need to know you've probably heard before, but we're going to label them and figure these out today together. Amplitude. So that's the farthest distance, the maximum distance that those particles of a wave's medium can vibrate from what's called the rest position. So what is the rest position? That's the part where the particles are going to sit. The particles of a medium will stay, right, when there's no disturbance. So there's nothing happening, right? So I asked you guys to take a look at what a wave would look like. Let's look at this here. So you drew something like this, hopefully in your notebook, which is what I asked you to do and send me a picture of. The troughs and the crests are here. So here is a crest, here is a trough, here is a crest, here is a trough. Look where the rest position is. That's that dotted line that goes across. So we measure amplitude. So the farthest away that it can get from the rest position right here where these arrows are, and then down here where these arrows are. We could do it here and here, and we could also do it here and here. So it says the amplitude of a transverse wave is measured from the rest position to the crest or from the rest position to the trough. So that might be part of what you drew in your notebook. Now we also have to talk about wavelength. We can mark on the wave from one point to another on the next wave the identical part. So we could measure, for example, from crest on one wave right here to the crest on another, or we could measure from trough to trough. So it would be something that we would have to mark that way. So one thing I want to mention that I didn't up here is that the larger the amplitude, so the farther away it is from that rest position, right, the more energy that wave carries, and that's going to be important later. And then when you think about the wavelength, so again, crest to crest, trough to trough, something like that, you can see that the shorter the wavelength, the more energy the wave has. So it's a little bit different. So here you can measure from the beginning of a compression to the end, or from here you can go from the beginning to the end, or from one spot on a compression to another. That's just another way to measure the wavelength. And again, the shorter that wavelength is, the more energy it carries versus the amplitude. The larger, the more energy it has. So they're two very different things. So again, you can see crest to crest on this one, trough to trough on this one. The only difference is this is a transverse wave down here, and the one above it is a longitudinal wave. So we also talk about frequency. In fact, you tune into a specific frequency on the radio when you're listening to like 104.1 or 105.1 or whatever stations you might listen to on the radio. Those are going to be measured in what we call hertz. So that's the number of waves that are made in a set amount of time. So for example, how many waves in a second? And that's a specific measurement that we make. So 1 hertz is a wave per second. So the higher frequency something is, the more energy it carries. So if you're tuning into a higher frequency, that is a more energetic wave. So they give you this example here. Speaking of frequency, so it says frequency can be measured by counting how many waves pass by in a certain amount of time. Here, 2 waves went by in 10 seconds. So the frequency is 0.2 of a second, or 0.2 hertz. So again, the waves are going to move by this person in the tube, right? They're not going to move with it. They're going to kind of have the waves come above them and pass them. So that's a good piece to look at too. So wave speed is something that we can calculate. And I do want you to spend a little bit of time with this. So how fast does the wave travel through water versus air? You'll notice that it's not going to be the same thing. So we take, information that we have, wave speed, frequency, wavelength, they're all related. And if we know 2, we can find the other one. So that's what we would do. And we may spend a little bit more time with that, but that's what we'll cover for right now as far as that goes. So make sure you have this all written down and that you're doing a good job of keeping track of this information for an eventual test. We will also talk about any questions that you have when we meet up.